you can see that the first value, the first coefficient is 0. So the coefficient of d to the power 0 will be 0. So we will get only d and the d square, because this is only 1 and 1. So G2D is d plus d square. So this is my impulses corresponding to C1 and C2. Right. Now what we have to do, GD, the ultimate GD, we have to write it, this G1D and G2D side by side. I have already told you how to write this total or ultimate GD. So GD equals to 1 and d plus d square. And MD, the message you will be given. So this is in the bit form. So 1101, this is your message. So this is your message 1101. So we have to convert this 1101 to the d polynomial again, because whole the procedure, whole the calculation will be in the polynomial form. So that's why the heading is polynomial description of the convolutional code. Okay. So just erase it. Okay. So when I convert this bit form of the message in the d polynomial, so you can tell me that what is the bit form? Message equals to 1101. So when I'm converting this in the d polynomial, so this is the first coefficient will be 1. So 1 into d to the power 0. So it will be 1 plus the second coefficient is 1 also. So 1. So here 1 dot d to the power 1, and d square coefficient is 0. So it will be missing, and we will get d3. So this is d3, right? Okay. So from this conversion, I am getting the message in the d polynomial as 1 plus dq. Now, so we have got GD, impulse response, and we have got the message. So what to do? We have to just multiply each G1D and G2D individually with message bit or message polynomial MD. Okay. So for C1D is G1D with MD. For C2D is G2D with MD. So this is G1D. 1 is basically the G1D, and d plus d square is the G2D. Okay. So 1 multiplied with this message, so it will be message. So C1D equals to message, and C2D will be multiplication of G2D with MD. So by multiplying this, we will get this d plus dq plus d to the power 4 plus d to the power 5. Okay. Now I've just written this C1D and C2D in this form. This is 1. The coefficient of d to the power 0 for C1D equals to 1. So that's why this is 1. Let me sketch it. This is 1. Now the first coefficient, or you can say the coefficient of d to the power 0 is 0 for C2D. So that's why this is 0. So this is 1, 0. For the second case, for d to the power 1, the coefficient is both 1, 1. So that's why this is 1, 1. Then again, d squared term is missing for both C1 and C2. So that's why this is 0, 0. And now d3 present. So 1, 1. Again, d4 is absent for C1. So that's why this is 0, and this is present for C2. So that's why this is 1. So this is 0, 1. And same as d5, because the coefficient of d5 of C1D is missing. So that's why this is 0. And for C2, this is 1. So in this way, you can write the ultimate result or the final result of C. So that is your code word. So this is your final code word. Okay. So let me just erase it. Okay. So what we have seen, that you will be given a message. You will be given a message in the bit form. So you have to convert in the d polynomial. You have to calculate the impulse responses corresponding to C1 and C2. That means C1 and C2 will be given in the diagram. So you have to make this table first to calculate G1 and G2, which is your impulse responses corresponding to C1 and C2. And you have to use this M message as unit impulse. The first bit will be 1, and rest of this will be 0. And that is basically the right shift register is used. So this is right shifting is happening for S1, S2. This is 2 registers. This is the present states 0, 0, 1, 0, 0, 1, 0, 0. Okay. So from that you will get G1D and G2D. Then you have to write the final impulse response as side by side G1D and G2D. So you have already converted message to the D polynomial form. Then C1D and C2D just multiplied with G1D and MD, G2D with MD. Then you have to write the final answer, the final code word with this coefficients of C1D and C2D. So in this way, we are getting result. This is the final result. So this is your polynomial description of the convolutional code. Okay. Now the thing is that we are showing here a new diagram. You have already known to this diagram because I have already shown you that this diagram is called FSSM. This is also called FSSM, or you can say finite state sequential machine. This is right shift register. It is also right shift register. So in the previous lecture, we have seen that from this encoder, or you can say FSSM, we have made this table. This is the present state, next state, and output. Okay. So you can also make this table with this diagram. Okay. So I'm just taking this example. S1, S2 is present. C1, 2, and C1 and C2 for the J instant. This is the output bit representation, and this is MJ, the input bit representation. So, and you can see there is a 2 XOR. There are 2 XOR. That means this is and this. Okay. So first of all, you have to make this table. So this is nothing but you have to consider this M message, present state, next state, output. Present state of delays S1 and S2, next state of S1 and S2, and corresponding output. Okay, this you have already done in your digital class or digital electronic class for the counter chapter. In counter chapter, you have to make this table, this kind of table, and you have to show the state diagram of the counter. Okay, so there was a modulo 6, modulo 2, modulo 4, modulo 9, modulo 10. So this kind of examples was there. So for the digital class. So here also, this is the present state. So I am using 2 delays. Okay. So this is 2 delays. I'm just recapitulating it because I've already studied you the state diagram, how to represent the state diagram. So this is basically the recapitulation. So this is S1 and S2. So 2 delays are there. So the possible combination of the state of delay will be 4. 0, 0. That means this 0, 0, 0, 0, 0, 1, 0, 0, 1, and 1, 1. Okay. So there will be 4 possible state of delays. Okay. So this is present state. So just let me.